Hello, everybody, and welcome to this month's Footsteps to Mars. I almost said Future in Space. Footsteps to Mars Hangout. My name is Tony Darnell from DeepAstronomy.com, and today we're going to be talking about using resources that already exist on Mars that may help us get to Mars. It's called ISRU. Oh, no. That was my fault this time. And today... There's been so much going on. It's like crazy. Some hangouts are easier to start than others, folks. So bear with us. We're still having people with technical difficulties, and so we were sitting around wrangling all this different stuff. Let me start again so that I can edit that bit out for those of you who are not watching live. Hello, everybody, and welcome to this month's Footsteps to Mars Hangout. My name is Tony Darnell, and today we are going to be talking about ISRU, which stands for In Situ Resource Utilization. Big fancy acronym because this is, after all, a NASA endeavor, and we have to have acronyms if we're going to be going anywhere with NASA. And we're going to be talking about what that is, but basically it's all about the idea. We've all heard the phrase Mars is hard. Getting there is hard, and most definitely living there is going to be hard, but we've got to start to think about how are we going to Mars, and in what capacity? Are we going to just visit Mars, maybe camp a few days and then leave, or are we going to stick around for a while, which means figuring out what Mars has to offer and using that. And we're going to talk about the pluses and minuses of both approaches, and we've got people from a variety of NASA institutions who are been thinking about this and working on it, and that will be the topic of today's discussion. But before I introduce my guest, let me introduce my co-host, Dr. Harley Thronson. He is from Goddard Space Flight Center. Hi, Harley. How are you doing?
Doing well. Good afternoon, everybody.
Oh, I can hear and see you. I can't tell you what a relief that is. That's good. And so, and I see our little rubber ducky in the back too. We're going to have to work that
bring
in.
out the rubber ducky.
Yeah, that's right. We got our little mascot there. So yes, and so I want to also mention that these hangouts occur every Thursday at 3 p.m. with the theme being something different, and they're all endorsed by the American Astronautical Society and the American Astronomical Society. These are the two AASs. And while the opinions and views expressed here are, while the hangouts are endorsed by these organizations, the opinions and views expressed on these hangouts are not necessarily endorsed by them. So I wanted to set that up. Also, this is a hangout on air, which means that we want you to interact with our guests. We want you to talk with us. The best way to do it is go to deepastronomy.com/live. I've got the live chat set up, and people are joining. I see some regulars. I see George Caldwell, for example, and a few other people there ready to go. So it's good to see you guys joining us. Another way to do it is to go on Twitter and use the hashtag Footsteps to Mars. I'm looking on that as well on my tweet deck. So those are the two ways you can ask our guests some questions. We hope you'll have some questions and comments for these guys getting and going forward. So without any more ado, let me introduce our guests. Well, first up is Dr. Jerry Sanders. He is the capability leader. Is that what I wrote down? Yes, the capability leader for ISRU at the Johnson Space Flight Center. Hi, Jerry. Welcome. It's good to see you.
Good to see you too. Also, as much as I like to play a doctor on TV, I only have a bachelor's degree.
Oh, forgive me. Okay, thank you for clarifying. Okay, so and so he is but he is the capability leader. I like that job title. That's really kind of cool. Also joining me is Dr. Dianne Linne. She is a senior research engineer and project manager for the ISUR Tech Project at the Glenn Research Center at NASA. Hi, Dianne. Welcome.
Hello, welcome. And I'm going to have to admit also that I just play a doctor on TV. I also don't have my doctorate.
Okay, well, thanks for clarifying that.
Yeah.
As I mentioned,
low to get into ISRU.
Right, that's right. So as I mentioned at the top of this, we had a lot of difficulties. I did not get to do a lot of the things I ordinarily do before a hangout begins. So, and one of them is to clarify that particular point. So thank you guys for doing that. I appreciate it. Okay, going to Mars. We all want to do it. We all want to go. But as we've been told by many different people, it's hard. Mars is hard. Getting there is hard. And launching rockets and stuff to get there is hard. But we want to think about once we're there. And so, Dianne, let me start with you and give us some of the ways in which you guys are thinking about this problem of once we're at Mars, and presumably that's where this mission picks up, right? In situ resource utilization means at Mars, correct?
Well, in situ can be anywhere we're going, but since
I know that, but in this case, Mars.
This is the footsteps to Mars. Yes, we're talking about using the resources at Mars to pretty much help us get home. So a lot of people talk to me and they say, "Oh, you're working on getting to Mars." I said, "Well, not so much. I'm just working on getting us home from Mars," which, you know, most of our travelers really have an interest in getting home.
And living on Mars while we're there.
So yes, we're talking about, you know, what can you look at, the atmosphere of Mars, the soil, the water in the soil. How can we extract that and make something useful out of it? And of course, the first big useful thing we need is propellants to get you up off the surface of Mars. And so that's one of our primary focuses, but there's a lot of other ones for, you know, as we want to stay longer and longer.
Do you mean as far as generating the propellants from Martian resources to get us up there, or bringing them with us?
No. So, you know, a lot of times when I talk to the kids when they come on lab or something, and I say, well, when you go on vacation with your family, like out to California, of course, I live in Cleveland, so that's a long ways. I said, you guys pull a tanker of gasoline behind you up over those mountains. And they look at me kind of confused, and they go, well, no. And I say, well, what do you do when your car runs out of gas? And after a lot of thinking, they say, well, we stop at a gas station. And I said, well, exactly. And because it would be silly to try and drag that gas over the mountains. And but that's the way we explore space right now. So what we're trying to do is basically build gas stations on the surface of Mars.
Great. Okay, good. And so with Jerry, with the things that you're working on as the capability leader, what are some of the things you're thinking about with respect to this problem? Just sort of give us a broad overview.
Well, like Dianne was saying, in general, we're trying to figure out how we can use resources to either make the missions more efficient or enable new things. And as Dianne pointed out, one of the big challenges and one of the big benefits to ISRU deals with when you make something there versus bringing it from Earth, like the gas station analogy. That means that your spacecraft launching from Earth can be lighter, which means that it takes less propellant to get there in the first place. We use something called a gear ratio, which says for every kilogram you land on the Mars surface or on the lunar surface, whatever, it takes a certain amount of propellant or payload mass to be launched into low Earth orbit.
Okay.
And what we have found is, depending on your process, it could be anywhere from 7.5 to like 11 kilograms. So if I'm making if I need 30 metric tons of propellant to get my crew off the surface of Mars back into orbit, and you multiply that by that gear ratio of 7.5 or 11, that's equivalent to eliminating something on the order of 3 to 5 heavy lift launch vehicles. So the idea is, you know, what can we do with those resources to help reduce what needs to be carried from Earth in the first place,
right?
Or enable new things. And propellant is one of those. We'll probably talk about life support consumables or you know, fuel cell reactants, things like that that can also be done. Eventually building habitats, roads, landing pads, etc.
That's right. And I'm going to get to that. But first, I'm seeing some people on chat saying, can you get rid of the echo? Can you please tell me on chat if we're still echoing? Because I don't hear it. If you are still hearing it, please let me know, and I will start muting people to get rid of it. So B. Siegel, you were the one who had done that. And Big Norge is doing the chat. Is this the Big Norge that I think of? Oh, man, this would be great. It's good to see you again. I haven't seen you in a while. So welcome, guys. Welcome back, Big Norge. Okay, so you were talking about leveraging things. I want to show this. I want to show this graphic that you guys sent me that I think is really a good segue into some of the things that you guys have just been talking about, and that is this cartoon here, where we're looking at whether we're going to carry things along or if we're going to use them as we go. And I like this analogy of, you know, back in the pioneer days when we were scheduling to go, or we were exploring this very large continent, to bring this kind of stuff with us, would have been a real problem, right? Is that, so Jerry, you want to explain this graph just a little bit to us?
Actually, let Dianne do that, because
okay, I'll let Dianne do it then.
Created this
sorry,
early on in our joint work for ISRU back in the early '90s, I believe.
And this goes back to what you were saying about do you carry gas? Do you know, when you run out of gas, what do? You know, when you're traveling.
Right, and yeah, I'm not even sure where this came from, but this is one of my favorites. Some engineer with you know, a lot of time on their hands said, well, if the mules that used to pull those covered wagons had to carry all their hay, all their water, and all their oxygen, and they figured out, you know, how much each mule you know, eats and drinks and breathes a day, and how far a mule can travel each day, and how much they can pull. And it basically said the maximum range is, you know, about 100 miles before they all die.
That's right.
And so we pretty much would have gotten about to the Appalachian Mountains, and that would have been about it. But of course, the pioneers knew all about in situ resource utilization, because they, you know, drank the water from the streams, and, you know, the mules ate the grass, and luckily the air happened to be very breathable for them. So yeah, this is one of our favorites, showing how important it is to relearn what our early pioneers already knew.
Well, I like that comparison, because it really is a good way to think about this, because the problem, of course, was a lot different back in those days. They, you know, and comparatively, the technology was simpler to go along with that. It was, you know, they knew that they didn't have to worry, the pioneers, that is, when they traveled out to a distant land, that they would have run out of oxygen. So they didn't think about that, but they did have to think about what they were going to eat and drink. They couldn't just bring all of it with them in any sort of practical way. And so this, I think, cuts to the heart of when we get to Mars, it limits a lot of things, right? How long we can stay, whether or not the nature of the mission. And so with you guys at the ISRU project, are you thinking, is this guiding the kind of mission that you guys are planning to go to Mars? I mean, first, you know, carry all the stuff with you versus in situ resources. Do you understand what I'm asking? Does this, where are you headed with the kind of mission, I guess, is where I should go.
I think one of the things, if you go back in time a little bit, you know, during Constellation program, for example, was when we really started promoting in an architectural sense. We've considered, you know, ISRU for Mars applications, DRA or DRM 1 to 5, and lots of studies have been mentioned, but it wasn't until Constellation, to a certain extent, that we really started to dive into, you know, how is ISRU used? Is it considered up front? Is it an add-on? Whatever the case may be. And that kind of philosophy drives, to a certain extent, decisions. You, at the beginning of your architecture, whether you're going to go to the moon or Mars, you have to consider, you know, are you going to use the resources there, and if so, under what circumstances? Because decisions you make on your transportation elements, on your habitats, on your power systems can be directly influenced. And so,
well, it seems to me that there's no way we're really going to be able to go to Mars without doing something using the resources there, right? I mean, I can't imagine there's an actual mission going that will just try and go there, carry all the stuff it needs, and then come right back.
Well, you can, to a certain extent.
You can do it. I mean, is that really practical?
It may not be logical. You can always do things by bringing everything with you. Obviously, Apollo, you know, the Apollo mission to the moon did that.
That was a much different mission.
So the challenge with Mars, of course, is that the gravity is twice basically what the moon is. And so you need a lot more propellant to get off. And it's also harder to land things because of the, you know, higher gravity. You know, if you If you come down too fast, of course, it's easier to crash. So because we need a lot more propellant, it would be a lot harder to do it without ISRU. We probably don't know how to land 40 tons if we landed a fully fueled ascent vehicle. So if we did it without ISRU, we'd probably need to still land in stages. You'd have to have multiple landings to get the ascent vehicle there and the propellant, and then you'd still have to somehow put those two together. Whereas with the ISRU, you can land a relatively light production plant right with your ascent vehicle, and then take your time while the people are getting there to make your propellant. So can we do it? Yes, but it's not a straightforward land the whole thing loaded like we did with Apollo because of the higher gravity.
Yeah, and I just want to make the distinction that the other alternative, if you don't carry it all with you, would be to send it all ahead of time, right? We've talked to people who are doing that as well, or at least planning for that as well. Correct. So we send fuel tankers out there. We send habitation modules and things out there that are waiting. That's the third?
Well,
there's bring it with you. There's use the stuff that's there, and there's sending stuff ahead of time.
or an optimum mixture of the three, which I think is the direction that most of the designs are going toward.
Like some sort of so
yeah, some things you definitely want to have there when you get there. Some things you want to, as we're going to be hearing more from Dianne and Jerry, you are much more efficient to make it there, and then some you have to take with you. There's unambiguous that you have to take some things with you.
And to a certain extent, that gets to the idea of mission risk. And so if you look at the design reference missions for human exploration of Mars, going back to even the first mission, the idea was, okay, if you take the Apollo approach and you send everything there, then you're comfortable that it's in place and in theory it works.
You don't lose it.
Once ISRU was introduced, then people were saying, well, I can't send my crew there because if they can't make the ascent propellant, how do they get home? So the idea was, okay, you pre-position it. One Mars opportunity ahead of time. You make your propellant before the crew ever leaves Earth, so it's all loaded up and filled. And to again reduce the mission risk. I think that was the approach that was mentioned in the movie The Martian, for example. They pre-deployed the lander for the next human mission, and it was going to make its propellant before the crew ever showed up.
Yeah, and I can imagine that would be a really bad day on Mars to find out that you were planning on making your own fuel only to find out you can't, and then you're really stuck. So yeah. All right, well, let's talk about what's easy. What are the most practical items that would be used, that would be found on Mars, that would be utilized, and then what are the more harder ones? So I guess, do you want to comment on that, Dianne? What would be the biggies, the easiest ones to use?
So the first thing we're talking about making is oxygen out of the atmosphere. And the reason why that's relatively easier is because the atmosphere is just there. Wherever you land, you've got atmosphere. And now the atmosphere is 95% carbon dioxide. So we can pull one of the two oxygens off of that and use that then and liquefy it and store it for your ascent propellant. There are, of course, some challenges. It's not as easy as that. The atmosphere, while it's there, it's only about 1/100th the pressure as it is on Earth. And so the first thing we have to do is somehow compress that before we start processing it, just so our reactors can be smaller. And one of the simplest ways we know of pulling that oxygen atom off is something we call solid oxide electrolysis, which is we call it a thermoelectric catalytic process, which means you got to apply a potential to it. You need the right catalysts on your solid oxide device, and you need a lot of heat, about 800 degrees C. But the technology is not totally unknown to everybody listening. Your oxygen sensor in your car, in your automobile, is basically a solid oxide device, except we're not electrolyzing CO2 in that case. We're just passing the oxygen through. You actually break the oxygen down into ions, give them some electrons, you pass it through the device, and then you give the electrons back up. So for every O that passes through, you carry 2 electrons, and by measuring the current, you can measure how much oxygen is coming through. So we use these devices in cars. We just have to, amp up the power and the temperature so that it'll electrolyze the CO2 first. But that's the first thing we're going at. Relatively few moving parts. The oxygen, we know the CO2 is going to be wherever we land. And so, also oxygen is about 3/4 of the propellant that we need in the ascent vehicle. So it's the first big mass that we can reduce.
Okay, so what's the second big component? You said oxygen
Well, before you mention that, before you go on, Diane, it's worthwhile mentioning that the MOXIE experiment that is being designed for the Mars 2020 rover is going to test out those technologies, how to collect and compress the Mars atmosphere and how to turn it into oxygen using a solid oxide electrical device. Obviously, the power on the Mars 2020 mission is not that great in comparison to what you would do for a human mission. So the production rate is on the order of about 1/100th of a human mission. But the basic technology that Diane just talked about is going to be
what's it called again?
Hopefully demonstrated.
What was it called again?
The experiment?
The experiment is called MOXIE.
Okay, and this is going to be part of a
oxygen ISRU experiment.
I see. Okay, and this is more of one of those Pathfinder kind of things, right? You're testing out the technology to make sure it works.
Yeah.
Okay, and then you can.
So go on, Diane.
Okay, so yeah, I just wanted to ask about the other component to the fuel. What was the other part?
Yeah, I was going to let you talk about the water, Jerry, if you want, the water and the fuel.
Oh, okay. Well, the next thing that besides the CO2 in the atmosphere, water on Mars is obviously the next big product or resource that we're interested in. The water can be found in several different forms. The most ubiquitous, or the one that's found throughout most of Mars, is in the dusty soil at the surface. Everywhere, pretty much. It's a very low concentration, something on the order of about 1.5% water. Depending on the type of mineral that may exist, it could be anywhere up to maybe 8% in certain clays and polysilicates. So one approach would be to dig up that topsoil, heat it up in some kind of a reactor, maybe on the order of a couple 100 degrees, 300 degrees C, drive off that water, collect it, and once you have water and carbon dioxide, you can electrolyze that water, turn it into oxygen and hydrogen. You keep the oxygen. The hydrogen and CO2 can now be mixed into another chemical reactor called a Sabatier reactor to make methane and water. That methane is a great fuel. So that's the other component of the propulsion system. So if I have water and if I have CO2, I basically can make oxygen and methane or any hydrocarbon, to be honest, depending on the chemical reactor.
And you said you were looking at doing that from the soil?
Well, there are different types of resources, and this gets back to that trade of do I find the resource anywhere at a very low concentration, or do I try to find higher concentrations of water elsewhere that may make my selection of the landing site a little bit more constrained?
Okay, I may not be on the right track. I'm going to put this up, and maybe this will tell me if this is adding to your discussion of what you're talking about right now. This goes back to your leverage and the gear ratios.
Yeah, this goes back to the gear ratio discussion more about how
okay, so this isn't
you
necessary.
land 1 kilogram, how it relates back to what you do on Earth.
Okay, all right. So
and the savings you get.
So you're saying that what you're discussing now is you need to really think hard about where we're going to land before we really think about reusing.
You have this chart with the football field on it?
Okay, hang on. I can bring that up. Here it is. Okay, and there it is. This one?
Yes. So the bottom right-hand side, we like to use football fields or soccer fields when we were working with the international.
We're saying.
To try to get across, you know, how much soil do we have to dig up, and what type of hardware would we use? And so to make the 30 metric tons of ascent propellant for the Mars mission, the oxygen and the fuel, you need something on the order of about 14 metric tons of water. If you have this low concentration of water,
what's up here?
Say 3%, you're pretty much digging up that football field down to a few inches over a year and a half. Now, as that concentration of water goes up, the amount of soil that you have to dig up drops significantly. So just going from, say, 3% to 5% water in the soil, you've reduced yourself down to excavating, you know, from the 30-yard line to the 30-yard line. Going up to 8%, you've reduced yourself from 40-yard line to 40-yard line. And then 30% or above, something like subsurface ice, you're literally just straddling the middle of this football field. So what we're doing is we're looking at, you know, what are the different forms of water on Mars? How difficult would they be to get? And how does that relate to the landing sites that we might want to go to for other purposes like science?
But it sounds like you're thinking ahead about all different possibilities of where you might end up. If you have a lot of water, then you're looking at not needing to excavate as much, or if you in the soil. And if you have less in concentrations, you're excavating more and more. So it sounds like it does the equipment change much depending on the water content, or is it all pretty much the same equipment?
No, it does change drastically. So
you still have to think about this before you go. You still have to think, well, where's our landing site characteristics going to be before you know what to even pack?
Yep.
Okay.
And to a certain extent, it's like prospecting. If you're going to open up a mine on Earth somewhere, you basically have to first of all look from orbital sensors or aerial sensors. Is the resource there? Then you send your geologist or drilling rigs to take a look at, you know, further defining that resource. What's the extent of the ore body? What's its purity and such? And then, you know, you start sending your hardware to open the mine. So it's kind of a very similar process that we're talking about here.
Okay, well, I want to get to what this is going to do to Mars in just a minute, but I guess this discussion of getting water, every time I've heard people talk about it, we've always been talking about ice. You know, we need ice. We should go somewhere where we know there's water and lots of it. You guys are talking about the soil. This is the first time I've heard about this. Wouldn't it be smart of us the first time around to just make sure we land near some ice? And wouldn't that change the equipment that we send?
Yeah, there's pros and cons to everything. If you can prove that the ice is there ahead of time,
well, okay, so
that is an option. But you have to consider, where is the ice and how difficult is it to get to it? The good thing about soil is it's on the surface. It may be relatively easy to excavate, whereas the ice may be 3 to 10 meters below the surface. Ice is obviously a lot harder.
So I just
and it would require different technologies.
So we talked about this before we started, and I wanted to bring this up at this point, where just last month, November 22nd, the JPL guys found this large ice deposit that holds as much water as Lake Superior. Would this revelation, would this discovery change? Is this, well, first of all, is this accessible ice in your opinion, or do you know much about it?
Well, I mean, if the relatively near surface ice, they mention, you know, that the overburden could be as little as 1 to 3 meters, and you're in that third paragraph below the blue box.
Yeah. Down here.
You know, if it's 1 meter, then yes, that could be relatively accessible. If it's 10 meters thick or more, that opens up some
you might want to bring some drills instead of. You might want to bring drills instead of a
extra shovels. Bring extra shovels.
Yeah, instead of an excavator or something. Yeah. Okay. So
as Dianne can mention, we're actually going through the analysis of the hardware, what type of infrastructure is needed, how much energy goes into that infrastructure to get that resource. And so, for example, when we did our latest study, even the low percentage of water in that topsoil, the 1.5% water, was actually more mass efficient to excavate and process the soil to get that water than it was to bring the 6.5 metric tons of methane from Earth and just making oxygen. So the benefit was huge. So now we're going to compare, well, what's the power system and what are the technologies needed to get that ice? Is it as beneficial as just digging up low quality dirt right at the surface? There's when you look at mining on Earth, and you look at the history of mining, you always went towards the top easy material to get to begin with, whether it was coal mining or iron ore or whatever. You started with an open pit mine, and eventually over time you started digging deeper shafts and doing subsurface mining, because either the surface resources were gone or the infrastructure versus your product economical. So it's really an economic study that we're doing now.
Yeah, I can see that, and it's also
another thing to think about that we haven't talked much about is the time we have to make this propellant. We talked about we probably send the ISRU plan out one opportunity ahead of time, and because you can only get to Mars about every 26 months, we actually have a lot of time to dig, and that's different than excavation here on Earth. Usually, time is money. You want to go in, you want to dig your hole, you want to get it out. But that's why those analogies on the football field. Not only aren't you digging up that much, but you have a couple of years maybe, or a year and a half at least, to dig it up. So that's another reason why, yeah, we might be processing a lot of dirt, but you don't necessarily, it's not necessarily an automatic answer that going for the deeper, more pure resource is the way to go.
And it's also a compromise. You want to kind of get as many resources accessible as you can, right? You want to get this soil with the higher water content, like you were pointing out, as much as you can, but you also need to do other things. We've been talking about fuel, and obviously extracting water will help people, will mean that we have to carry less of it with us when we travel, when we on our supplies going forward. But I want to talk a little bit about food. What's is the Martian soil something that you can actually farm in? Or we all saw the Martian, we saw what he did, and you can comment on whether you thought that was realistic or not. But are there any plans on using the soil perhaps to grow any food?
Jerry,
there's a lot of quiet out there.
Yeah, it's something that has been considered, but whenever you do anything with the crew, there are always extra steps that are required to verify that there would not be any issues associated with it. So, for example, if we extract water from the soil and we process it to make rocket propellant, that's one thing. If we extract water from the soil for drinking, you have to go through certification process that the water has been cleaned and whatever the case may be. Same thing probably is going to happen with plants. Dianne and I aren't necessarily in that area, but we work with the human, exploration folks and the different areas. And so maybe the first crew does some planting, just like they do on space station, where they don't necessarily eat the first crops that they've made. They usually bring them home for analysis or do some in situ analysis. Now, in the case of the Martian, if your life depended on it, you throw the rule book away and you do what's needed. but there's still a lot of questions about what form the Mars soil is in and what contaminants and what minerals are there. So a bit more work needs to be done before you just drop seeds into Mars soil. And
that's an excellent point. I hadn't really even thought about it much. You don't, just because there's water in there after it's processed, you don't necessarily want to drink it. You don't know what effects that's going to have.
And we've joked about the moon, for example, that there's been several papers that besides water at the lunar poles, there's also a fairly high concentration of mercury. And so a paper written back in the 60s said, don't drink the water, because they had already realized you have to do something with the mercury that may be there.
Okay. All right. Well,
I've got a question for our guests, which no doubt just occurred to me, but no doubt you thought about it, and that's the planetary protection implications of ISRU. And the depth of thought that I've had about it is the following. I wonder if a full-blown, very effective ISRU capabilities might mitigate some of the planetary protection challenges in sending humans to the surface of Mars, because you would not have to bring a whole lot of potentially contaminating materials to Mars. You could make your stuff there. It would not add contaminants to the surface of Mars, as opposed to the scenario, an optional scenario, where you are bringing a lot of stuff. But that was pretty superficial. Are there?
Well, I can imagine, Harley, the planetary protection guys coming down the hall and fighting with these guys over. You're going to do what? do you guys ever have those discussions? I mean, what is the balance that you guys have to strike? Because clearly you're going to have an effect on Mars once you're there.
So one of the discussions we do have, and this goes back to whether you would just go after the ice deposit or the higher water content, is that in the areas where there is higher water content or ice, that's the special region area where they might want to be looking for life or signs of past life and everything. So even though it might be a higher resource concentration, that might be the area where they tell us to stay away from.
Yeah, the recurrent slope Linne is a perfect example of that.
Oh, right. That was going to be the next question. Yeah,
we talked about that in the last Hangout. That's, maybe you could remind us what that is. That's those appearances of ice that come and go with the seasons, I think, right?
That's the theory, is that basically, whether it's perchlorates or whatever the case may be, the melting point of water has been depressed such that you see these channels of water forming and slowly moving down the slopes of the sun-facing slopes of different craters on Mars.
Okay.
And if it is water, then there is always the potential that has seasonal life to it.
So already I see a Mars National Park Service springing up where everybody is saying, okay, you can dig here and here and you can develop over there, but don't go over here and mess up with these regions over there.
Yep, that's almost already the case.
Yeah. Well, there's also treaties. We've talked about that. There's treaties about, how to behave and how to act over on these other celestial bodies. And so that all comes into play. Boy, the lawyers, I can see a whole new legal field developing out of this as well. Okay, well, I want to remind everybody that I am talking with Dianne Linne. She's a senior research engineer and the project manager for the ISRU tech project at the Glenn Research Center. I'm also talking with Jerry Sanders. He's a capability leader for ISRU at the Johnson Space Flight Center. And I've got a lot of questions coming up on social media. We're running out of time. I see Laura Forzik is back on Twitter, saying we need to purify drinking water extracted from Mars, but water for fuel needs to be purified too. Question is, how much? So do you have a sense of how much the water's got to be purified, whether it's for drinking or for fuel?
Well, for fuel production, it has to be purified to the extent of the processing hardware. So, for example, there are two ways you can break down the water into oxygen and hydrogen, and then use the hydrogen for subsequent hydrocarbon production like methane. One is what's called a PEM electrolyzer, proton exchange membrane.
Oh yeah, I have one of those.
You actually need to purify the water quite a bit, even greater than drinking water to a certain extent. To get rid of all the ions that exist that could break down the membranes and cause problems. Then there's the solid oxide electrolyzer that Dianne mentioned for CO2 processing. It works great for water as well. That water vapor could potentially be a little bit more dirty than the PEM electrolyzers, but in both cases, you have catalytic reactions, electrocatalytic reactions. And so you don't want to degrade those catalysts or electrodes in any way by having a contaminant. So from that perspective, we have it pretty well. From the life supports perspective, we're actually working with those folks and trying to understand their requirements a little bit better, because you actually have to add biocides to the water before you're allowed to drink it. So for example, you're not allowed to drink the deionized water that would go into a water electrolyzer.
Okay.
You actually have to put additives back in for safe human consumption.
Yeah, I can see. So yeah, depending on the use case, you're looking at a different varying means of doing the purification. So I want to get to some more questions. There's a lot on the chat, guys. Wow. And I've been reading it and getting distracted. I want to put up a pretty picture, and then I want my guests to talk about it while I go through some of these questions real quick. This is a concept that you guys sent of ISRU mission capability concepts. Can one of you talk about this briefly? And while I have this up, and I'm going to go through my chat window here and get some questions put together.
Okay, well, this is just, again, as you said, it's a concept. There's a lot of different concepts. So you would have in the upper right corner there's your lander and ascent vehicle that you would be filling up with propellant. In this case, they actually have the ISRU plant off to the side there. So this is more a concept of a more permanent base that you'd be coming to frequently. That's why we've built a landing pad underneath the lander and ascent vehicle there, and we've done that using our same excavators we're using to excavate for our resources. We've also built up a berm, so when you land, you don't shoot a plume out that's going to impinge against your habitat, which is over there to the left of the picture. In this scenario, you would be coming back to the same location, so you would be using the same plant over and over again. So you would have to have some kind of transport vehicle to transfer the propellant you made in the ISRU plant back over to the ascent-descent vehicle there. And then by this time, you would also be, of course, supplying the habitat with life support. And even the, I think there's a rover shown there. I can't see the picture. It went down to small screen.
Just click on my thumbnail. It'll get big for you.
Okay, there it is, the rover. So they have a large excavator shown there and some common rovers, but you could also be supplying the rover with power, maybe by providing reactants for a fuel cell to power that rover. So there's a lot of things going on as you progress, and maybe again,
I love the term common rover now. I can't believe we're going there with it. Oh, we just got it. It's a common rover, just your basic rover design.
Your basic chassis.
I guess my point was
is that we really wouldn't put all the hardware right next to the landing pad like this. This is a poetic license from Pat Rollins to try to cram everything into to one small picture.
Yeah. Okay. Well, so R.W. Moses, I want to thank you, by the way. I'm not sure who you are, but it sounds like you're answering a lot of questions for the guests on the chat, and I want to thank you for that. He goes, one comment.
Yeah, that's Rob Moses. He works at Langley. He's part of our team.
Oh, good. Welcome, and thank you for joining on the chat. This is very helpful. He makes a great comment. He goes, Hanley, I'm working with COSPAR I'll get to that in a minute, to address the planetary protection issues for Mars. We held a meeting 4 weeks ago at the Lunar and Planetary Institute in Houston. A report will be released soon. ISRU poses problems, as Dianne is mentioning, but there are solutions being discussed. What is COSPAR? Do you guys know? Hello?
Oh God, it's an
it's a meeting.
Professional society.
Okay, so
yeah, that's what I was reading.
Okay, but they're facing these issues they're discussing these issues that it appears about. You can't just go there and start digging up Mars for willy-nilly, right? So,
yeah, and we had a workshop at Ames, I believe in February of last year, even talking about planetary protection for human missions versus science missions. And it should be noted that habitats in EVA suits associated with the crew leak tremendously. And so the idea of having humans on the Mars surface and not having some level of contamination is not possible. You'll never get a habitat that's 100% leak proof. You'll never have an EVA suit. So you're going to be releasing gases from these areas that have Earth biological material. So before we send humans to Mars, there's got to be an agreement on the forward contamination aspects associated with bringing Earth bugs to Mars.
Yeah, because I think Alberto, we talked about that before. And when you're trying to find life on Mars or evidence of life on Mars, you want to do it way before we start going there. It seems to me like, because we're just going to start leaving DNA everywhere and all kinds of stuff, and who knows.
But Dianne actually hit an important issue, and that is when we talk about going for water on Mars, and especially high concentrations of water, that will raise issues about the search for life and what are called special regions, which hopefully we don't get into now, that need to be taken into consideration. And what type of ISRU hardware would you use? How much do you have to sterilize it and such? So these are things that we'll be talking about and working on for the next several years.
Yeah, and that explains a lot about why you guys are trying really hard to get it out of these lower concentrations of water from this regolith of the soil than you are about just going straight into one of these, sort of high potential for life areas and start doing all this. So that makes a lot of sense.
And another aspect to think about in all of these that we really haven't touched on, Dianne mentioned that we would be operating for potentially a year and a half before the crew ever shows up. Well, that gets into designing hardware that can operate autonomously. There are things you might be able to do in either case, whether you go for ice or for loose soils, but you have to design your hardware for potentially autonomous operations without crew being there. So a deep drilling rig, may raise more issues for autonomous operation than others. So we may take a evolutionary approach that we use one form of water to begin with, and then once the crew's there, maybe we do the deep drilling rig aspects, the Armageddon drill with Bruce Willis once the crew's there.
Well, that explains. Okay, so as we've heard many times, NASA's timescale is in the 2030s. So that kind of thing, where you've got to worry about these autonomous things working for a long time, that sounds to me like a perfect opportunity to send up. And this goes in line with what Ann Parsons is commenting on in the chat of rovers. You want to have these Pathfinder rover missions, right, that test out various kinds of technologies that would last for a long time. And so, is that one of the reasons, do you think, that NASA is planning such a longer time scale? We've got to test this stuff. We got to find out if we can even build machines that can run this long autonomously.
One of the things we've been talking about recently is out of all the systems we need for Mars, we've flown some form of all of them. We've flown chemical propulsion, even electric propulsion, if we're going to use that to get there. We've flown habitats. We've got the space station. We've done some form of landing and ascent vehicles. We've flown power supplies. We've flown life support systems. All these things. We've flown rovers. Both the human ones on the moon and the robotic ones. And the ISRU community has been pointing out to headquarters. We've flown everything in some form. Not saying it's easy and we got it all figured out for Mars. We've never flown ISRU at all. And so we're really saying that, we really like a demonstration mission, because we find it hard to believe that you're going to, rely on this to, save the astronauts' lives, basically, bringing them home. if you haven't flown something of a reasonable near scale.
Okay, well, let me ask you this, Dianne. Where would you start if you were running NASA and you were saying let's fly some ISRUs? What would you do first?
Well, so we're starting already with the MOXIE experiment that Jerry mentioned. It's going to fly on the Mars 2020 rover. So that's demonstrating a couple of the critical technologies, the pulling in the atmosphere and the splitting up the carbon dioxide, but a very, very, very small scale because of the size limitations. What we'd like to do is send up something that's about a 1/3 or 30 or 40% scale. We think we'd be more than ready to do that in the mid 2020s. Some of us, of course, who get really excited about ISRUs say that, well, if you're going to go and fly that and land that on Mars and make that propellant, you might as well put a little rocket in there and bring some samples back while you're at it so that you can demonstrate the whole end to end. So if I was running NASA, that would be aimed for somewhere in the mid 2020s, ISRU sample return mission.
Yeah, see, folks, I mean, we've in our Footsteps to Mars Hangouts in the past, we've talked about things like Elon Musk, and he's going to get us there in like the 2020s or whatever. But to me, it seems like this is the kind of stuff you need to be thinking about. What are you going to do when you're there? I think he famously said, I'm not worried about getting there. What happens when we're there, we're just going to get there. And you do need to think about all these other things, and it makes a difference in how long it takes to go. With these various technologies. And Ann Parsons, I'm just going to ask your question directly because it's a little bit different than the way I paraphrased it. She says, it would seem beneficial to send prospecting rovers to determine where the best locations are for digging. Do we need to do that? Do we already have a pretty good idea of where we want to land?
Well, there's a couple of things. First of all, we already have prospecting rovers on Mars.
Yes.
If you actually look at the Curiosity rover, it has a neutron spectrometer on board. It has mineral instruments. It has a oven that can heat up samples, and we've gotten data from all of those pointing to amounts of water and volatiles that are released when you heat the soils. The ExoMars mission, if it flies in 2020, will have a deep drill with many of the same type of instruments. And we have orbiters in place, so we have a pretty good knowledge of Mars per se. But just like the analogy I mentioned about mining, we do need more information. So if we are going to go for water on Mars in one form or another, then yes, some precursors, possibly joint science and human exploration, to check out landing sites. There was a workshop held, I believe, in February for it was called the first Mars human landing site workshop. So that discussion now is going on in terms of what are the landing site criteria that we would use for selection? How do we balance science exploration and resources and other aspects? Your landing capability. How flat does the terrain need to be? What latitudes are you allowed to land at? Those are all things that are spurring on a lot of discussion, and I believe there's plans for a second Mars human landing workshop.
Yes, I'm really glad you brought that up because that was one of our earliest hangouts for Footsteps to Mars. So look at the playlist for this hangout series. You'll see that was one of our first hangouts where we discussed what's going on in these meetings and the kinds of things that they're talking about, which is where I was going with that. So I'm really glad that you brought that up. A couple of things. Is his name Rob Moses? Is that what you said?
Bob, yeah.
Bob Moses. Okay. He's really been contributing a lot to the chat. Thank you so much, Bob. The COSPAR stands for Committee on Space Research. So thank you for clarifying that. And there was one question I wanted to, George Caldwell is asking, would the largest problem in getting to Mars and while on Mars, it scrolled past, from a human perspective, be the ionizing radiation? I don't know that that's quite fits in with the ISRU stuff, but isn't that a bit, does the radiation affect the kinds of resources that you would want to use at all?
Well,
Go on, Diane.
Well, actually, I was going to say that we do talk about radiation, but we talk about how ISRU can help with that problem. We've talked about, once our excavators are still there, and, once people get there, we're done excavating because we've made all our propellant. So we've talked about possibly, burying, piling dirt on top of the habitats if they're a hard shell to help with the radiation protection. Or if we're making water, and if we found that nice solid source of water where it's relatively easy to extract, you could build your habitat with a double wall, and you can fill that with water. Water is one of the best protections. Now, that doesn't help the people on the way there, but it certainly would help. You could make your habitat lighter, and we could add the radiation protection using some of our ISRU equipment once the habitat gets there.
Even make polyethylene for that matter.
Okay. Before running out of time, but I want to get this question in if I can. Rainbow Panda is asking an outstanding question. Will resources like platinum be mined or refined on Mars for use in chemical reactions, or will it take colonization for that level of ISRU? That's a good question. Anyone?
Probably the colonization aspect, because again, when we talk about ISRU capabilities, it's all about economics. What is the product, the amount of product that you're requiring versus the amount of infrastructure and energy required to develop that product? As Dianne pointed out, if it takes 1 metric ton of hardware to make 30 metric tons of propellant, that's a pretty easy comparison to economic case. However, if you're going to be mining platinum or extracting any metal for that matter, you have to look at what is your customer? How much do they need over how much time? So, besides making propellants, the next thing that we probably would do from a mass benefit perspective is along the lines of the radiation shielding or structures that could be added for protection and such. Okay. Eventually, we may make parts from crude metals that we can extract, but getting to the ability to refine high purity platinum to go into small catalytic reactors probably is much farther downstream.
Okay, and I want to end the hangout with this comment from Bob Moses on the chat. He goes, "We do not have a good idea where to land yet. Ground penetrating radar will help greatly to identify the pockets of water that offer the best opportunity for habitability and resources. The human landing site workshop identified 50 plus locations. These need to be reduced to 5 for sending rovers for due diligence of resources and habitability." So they're narrowing it down. A lot of work is being done. I want to really thank you, Bob, for taking some time out on the chat to answer people's questions. That really was a nice resource. So thank you very much. I also want to thank my guests, Gerald Sanders. He's the capability leader for the ISRU at the Johnson Space Flight Center. And Dianne Linne is the senior research engineer, project manager for the ISRU Tech Project at Glenn Research Center. Thank you both very much for taking the time out to talk with us. This is, I think, key to getting us to Mars. We've got to start thinking about not only what are we going to carry with us versus what are we going to use when we're there, but then there's all this planetary protection stuff. You don't want to just tear up Mars in critical locations. So I hope you guys will come back as you get more work done on this issue. This has been a real fascinating hangout. Thank you so much for taking time out to join us.
No problem. Thanks for inviting.
All right. Well, I want to thank you all for watching. That's it for this week, this month's Footsteps to Mars. Join us next week, where I'll be with Carol Christian and the Astro Coffee, where we will be talking about Dragonfly 44, which is a galaxy that is 99.9% dark matter. At least that's what they think it is. And we're going to talk about why they think that and the nature of this galaxy next week. So we hope you'll join us. And then after that, we've got our Future in Space Hangout on December 15th, which I'm hoping will be an update on the James Webb Space Telescope. But Harley is helping me set that up right now. So we're still kind of
very busy time of the month.
It is. And then we're going to break for the year. So, all right. Thank you all very much for watching. And on behalf of Harley Thronson and the Goddard Space Flight Center, I want to thank you. And I will see you next week. And as always, keep looking up.
And we have our mascot.
Right. We got to take him to Mars, or at least
Yeah.
make some while we're at Mars.
Leave them behind.
We'll make these. We'll make them in situ. That's what we'll do. Thank you, and we'll float them down little creeks and never mind. Anyway, thank you guys very much. Bye bye.
Bye.